Good evening, Algebra 2 students. This video will be overviewing trigonometry, and we will be going into the entire unit. But if you notice that, some topics we don't go into as deeply as we did in class, that's because this will be more focused on the kind of questions that the Regent asks, and more specifically the topics and skills that they're testing for. So if you might not see all the identities that we did in class, that's because the Regent doesn't cover all of those identities, right? But that's not to say that we aren't going to go deeply into the concepts that the Regent does test for. We'll definitely go into what each topic means, how you could go about solving each topic, what you could do to memorize some of these things, and little tips and tricks here and there. So let's start with, what is trigonometry? If I had to say it in only a few words, I would just say trigonometry is the study of right triangles. But why right triangles? That's because right triangles, the side lengths and the angles have special relationships, right? So in geometry, you might have remembered SOHCAHTOA. So we know, opposite, hypotenuse, adjacent, right? Those are all different types of sides of a right triangle. So we have this right triangle here. The hypotenuse is the side across from the right angle, sorry. We have, let's call this angle theta here. The opposite would be the side across from that is not across from the right angle. So this would be your opposite side. Your adjacent side is that neighboring side that is not across from the right angle. So, in SOHCAHTOA, what is SO, right? And SO is sine theta equals opposite over hypotenuse. Now, we will go more deeply into what sine, cosine, and tangent actually mean when you see, the unit circle and when we start graphing the trig functions. But right now we're talking about what trigonometry is. And we said that there's special relationships between angles and sides. This is a ratio of side lengths, a ratio of sides, a proportion of sides. If you had a specific number that quantified the side length of the opposite side, and you had a specific number that quantified the side length of the hypotenuse, that would give you a specific angle. So that, what we just said is, if you're given two side lengths of a triangle, you could figure out what the angle is, right? And the same thing goes for cosine. If you are given the length of your adjacent side and you're given the length of the hypotenuse, you could figure out what that angle is. Same thing for tangent. If you are given the opposite side and you're given the adjacent side length, you could figure out what this angle is. And that's really all trigonometry does. It establishes a relationship between the ratio of side lengths and the angles. So first, let's start talking about, rotational diagrams and angles. It might be, so from what we learned in class, students might struggle to make connections between how this is useful with, evaluating trig functions. And it's actually really inherent in every problem we do beyond this point. So I'll try to make the connections once we get up to that. So first, here, we have this angle in standard position. That's because the initial ray starts at the origin and it's along the x-axis. Positive and negative rotations. In math, a positive angle is going counterclockwise. A negative angle is going clockwise. So in this case, it shows that it's going counterclockwise. So that would be a positive angle. If it was negative, then it would be going clockwise. Coterminal angles. So this angle here, let's say we were at 0 degrees, not the angle that's drawn. Let's say the angle was at 0 degrees. How many degrees would I have to go before I got back to that point? You would have to go 360 degrees. So, is 0 degrees equal to 360 degrees? No. One angle went a full rotation around and one didn't move at all, right? 360 degrees is bigger than 0 degrees. But do they look the same? Do they land in the exact same spot? Yes. And that makes it coterminal. And that would go with any angle. If I would go from this angle another 360 degrees, that would put you in the exact same position. So coterminal angles, in order to find different coterminal angles, you could either add or subtract 360 degrees. And you'll see how that's useful in a minute. And then lastly, reference angles. And this is probably the most important vocab term for this entire unit. And it reads as the positive acute angle formed by the terminal ray and the x-axis. So in this case, the reference angle, we have our terminal ray, you have your x-axis. It's that angle made between the terminal ray and the x-axis. And you'll see how important that is when we're determining or when we're evaluating the trig functions or when we're graphing trig functions. Okay, so we have this question here. It says draw a rotational diagram and then state the alpha's reference angle, alpha sub r. So alpha equals negative 443 degrees. Now, this is 0 degrees, this is 90 degrees, this is 180 degrees, this is 270 degrees, this is 360 degrees, right? Does negative 443 degrees fall within any of those quadrants? Well, we know from coterminal angles that it will land there, but is it in between any of those numbers? No. So, we're going to have to find an angle that lands in the exact same spot as negative 443, but it's not going to exactly be negative 443, and that's why we're going to have to show the rotation, how many times it traveled. So, negative is less than 0, right? And we want to be in between 0 and 360. So let's add 360. I get negative 83 degrees. Does that land in between 0 and 360? No. So I'm going to have to add 360 again. And we get 277 degrees. So which quadrant would that land in? It would land in quadrant 4. So when we're drawing a rotational diagram, draw out your quadrants, draw your initial ray, draw your terminal ray, and it's negative. So is negative clockwise or counterclockwise? If we were to draw 277, right, that would be positive, so it would be counterclockwise, and that would be 277. But the angle we're trying to draw is not positive, it's negative. So we have to think about what we're doing. We start from the initial ray. Because it's negative, we're going to go clockwise. We go around 360. Then we're going to have to go another 83 degrees, right? So that angle that we just drew, the rotation diagram, was for negative 443 degrees. So that's actually alpha, what we just drew. We want to find the reference angle now. So we'll put the reference angle in pink. And we said that a reference angle is formed by a terminal ray and the x-axis. So we want to find this between the terminal ray and the x-axis. So we know that this is 360 degrees, and we know that this positive angle here would be 277 degrees. So 360 minus 277 would be 83 degrees. The reference angle in this case would be 83 degrees. Okay. Just to kind of, look forward to why reference angles are so important. If we were trying to determine the value, if we were trying to evaluate a trig function, typically we would make our right triangle, right? And the angle we find here, when we're finding the proportion of sides, we're finding it for the positive acute angle, right? That's your reference angle. But if we wanted to actually evaluate the trig function of that angle, the original angle, technically they land in the same spot, so they form the same right triangle. But the problem is 83 degrees is up here, right? So remember that acronym that we learned in class? I didn't really want to go into it yet. All students take calculus. Technically, you're going to find the same value, but depending on the quadrant that it's in, that determines the sign of that value. It completely changes the value. It's the same value if you're talking about the absolute value of it, but to determine the actual sign of it, you have to determine, which quadrant it's in. That's why reference angles are so incredibly important, because even though you don't actually, you might not even know that you're using them, that's what you're doing. When we create that right triangle, that positive acute angle that we're using is the reference angle. But typically we're trying to evaluate the original angle of a specific trig function. So that's why it's important that you remember the last step, if you do use the reference angle, is to check the sign by using all students take calculus. Again, we're going to get deeper into that in this video, but I just want to draw connections between why we learn this and how we use it, even if we're unintentionally using it. Okay. Radians and degrees. I'm going to do a quick little mini lesson on what a radian is. Do you really need to fully understand what a radian is for the region? No. So if you want to skip this part of the video, you can. I recommend, watching it. I'll try to be quick. So a radian is a unit of measuring angles. And all a radian does is it measures angles in terms of the radius of the circle. So for example, 1 radian is the angle produced at the center of a circle by an arc length equal to the radius of the circle. So, for example, the radius of the circle, the center is about here. This is your radius. If we were able to take that same length and go around the circle with it. That would be 1 radian, right? 1 radian is about 57 degrees, so that's what that would look like. Now, we know from, previous years of math, the circumference formula of a circle is 2 pi r, right? And we just said if it's in radians, it's in terms of how many radiuses we're going around the circle with, right? So the entire circumference of a circle is 2 pi r. Remember, pi is 3.14, so 2 times that is 6.28, right? So it's about 6.28 radiuses around the circle, right? So that means your circumference of your circle is going to be in terms of radians. So if we're talking about a unit circle with a radius of 1, right, because that's what a unit circle is, it's just 1 unit the radius, then you could just plug that in for the radius, and you would get that the circumference is 2 pi. You also know that a circle has a central angle of 360 degrees, right? Which means that the circumference is 360 degrees. So if the circumference is 360 degrees and it's also 2 pi radians, now you know that 360 degrees, or a circle, is just 2 pi radians. 360 degrees equals 2 pi radians. So let's say we found the proportion of those two things. Let's say we divided 360 degrees by 2 pi radians. You could simplify that, right? 360 divided by 2 is 180, so it would be 180 over pi. If you multiplied an angle in radians by that, the radians would cancel out, right? Because let's say you had x radians. Radians would cancel out, and you would be left with degrees. Now you have your angle in degrees. Let's say we did the reciprocal of that. 2 pi radians over 360 degrees. That would simplify to pi over 180. If you multiplied an angle in degrees, right? Let's say you had x degrees. Degrees would cancel out, and you would be left with the answer in radians, the angle in radians. So that's all degrees and radians are. If any of that confused you, again, you really don't need to understand the concepts behind it. You could just accept this as a fact. This is on your Regent reference sheet, right? Personally, the way that I memorize these two formulas, which again, they're on the Regent reference sheet, is we know that when something's in radians, usually, not always, it could be 1 radian, right? But typically with radians, you see pi in the answer, right? And with degrees, typically you don't see pi in the answer, right? So what I remember to do is I want to get rid of pi if I'm converting to degrees. So you'd be dividing by pi, and then it's just going to be 180 over pi, right? So what we just said was to convert from radian to degree, you multiply by 180 over pi. With degrees, typically there's no pi in degrees, right? So if you wanted to convert that to radians, you want pi to be there, so it's going to be in the numerator. And then it would be pi over 180 that you're multiplying by. So that's just one way to memorize it. Again, you don't need to memorize this. It's on the Regent reference sheet. So, again, if any of the concepts behind it confuse you, you really don't need to know all of that. You just could know to multiply by this, multiply by this. So we want to convert this degree to radians, right? And if you're converting from degrees to radians, remember, there's no pi there usually, right, for degrees. So we want there to be pi. It's going to be in the numerator. In my calculator, I'm going to do 114 divided by 180 I'm going to convert to fraction, and I get 19 over 30. Is that right? No, I forgot the pi, right? Just don't put pi in your calculator, because then you're going to get a crazy irrational number. It'll just so happen that you have what this equals as a decimal, but you want to express this in terms of pi. Now, to convert this radian into degrees, right? Look at that. It has pi in it. We know radians typically do have pi in it. So if we wanted to get rid of the pi, you would have pi in the denominator and 180 in the numerator. Again, if that confuses you as well, this is on the read and reference sheet. Just know that you have to use one of the two, right? So, pi cancels out, and I could put that in my calculator. 89 divided by 45 times 180, you get 356 degrees. Okay, for the unit circle, I could teach you how to memorize this, or I could go into the concept behind it. First, let me teach you how I memorize it. I memorize it as 3, 2, whoops. So 30, we start at 30, 3, 2, 1, 1, 2, 3. They're all over 2. And they all have radical in the numerator. It's okay that I put radical over the 1, because square root of 1 is just 1. But you could leave it as just 1/2 as well. Right? That's how I memorize that. And then these points are easy because you know it's a unit circle. So the radius is 1. So this would be 1, 0. This would be 0, 1. This would be -1, 0. This would be 0, -1. Right? Now, I don't memorize these quadrants, but if you look, they have the same y value, right? And it's going to be the same distance away, just negated. So you're going to be negating the x value. And the same goes for all of them. Right? Something else you might notice. In this quadrant, a point would be negative and positive. In this quadrant, a point will be negative, negative. So you're going to have negative, negative of both. In this quadrant, you would have positive, negative. Right? So that's another way that you can memorize that. Right? But I would like to show you how to derive these. Do I recommend, wasting time to derive them? No, but for, life's sake, if you go further with math, it is good to know where this stuff comes from. So, again, let's start with the easy points. This is 0, 1. Whoops. 1, 0. This is 0, 1. -1, 0. 0, -1. Now, again, trigonometry, study of right triangles. So let's make a right triangle. So I'm going to redraw it over here. And the one we're looking at right now is 30 degrees. So we have this 30-degree right triangle. And we said it's a unit circle. And the unit circle has a radius of 1. Now, we have the 90-degree angle. We have the 30-degree angle. We know the sum of the angles of a triangle add up to 180. So 180 minus 30 plus 90. Or you could do 180 minus 30 minus 90. you're going to get 60. So, what would happen if I reflected this over? If I reflected this over, this would be another 30, which makes it a 60 degree. This would be 60 degree because it's a reflection. This would be 1, 1. They all have the same angle, so we know it's an equilateral triangle. So that would be 1. Half of 1, if we're looking at the original triangle, would just be a half. Now we have two sides, right? And a right triangle. So we could use Pythagorean's theorem to solve for the other side. So a squared plus b squared equals c squared. We have x squared plus 1/2 squared equals 1 squared. Subtract 1/2 squared, or subtract, 1/4. And we have x squared equals, this is just saying 1 minus 1/4, which is 3/4. Take the square root of both sides. X equals the square root of 3. Square root of 4 is 2. So square root of 3 over 2. So let me redraw the original triangle we have here. We said that this was 1, this was 1/2, and we just learned that x is radical 3 over 2. So this point, the x value is that side length, so that would be radical 3 over 2. The y value, the height, would be 1/2. Right? So, let's do that again, but for the 45-degree angle. We're going to make a right triangle. Okay, so I'm going to do 180 minus 45 plus 90. You end up getting 45 degrees. Now you have two angles that are the same. What kind of triangle has two angles that are the same? Oh, an isosceles triangle. And if you remember from geometry, the isosceles triangle theorem states that the sides across from the equivalent angles are equivalent. So this equals this side. And didn't we say this was a unit circle? So what was the radius of the unit circle equal to? Oh, that's right, 1. So we could use Pythagorean's theorem, a squared plus b squared equals c squared. X squared plus x squared equals 1 squared. That's just 2x squared equals 1. Divide by 2. X squared equals 1/2. Square root of both sides. X equals the square root of 1 is 1. Square root of 2 is 2. Now that doesn't look like any of the things that I said you could easily memorize before, right? And that's because you could do something to kind of manipulate this a little bit. You could radicalize your numerator. If you multiply by the radical in your denominator over the radical in your denominator, right? You have to multiply by 1 so that it's the same number. You would end up getting radical 2 over... Now radical 2 times radical 2, isn't that just the same as saying radical 2 squared? The square root cancels out. You get radical 2 over 2. And this one's actually even easier because we have an x and an x. So we already solved for what both of those x's equal. Radical 2 over radical 2, radical 2 over radical 2. So we get radical 2 over 2, radical 2 over 2. The x equals the y. The length equals the height, right? So now, we're not even going to have to do this again. You're going to see why right now. Let's make our right triangle. You have a 60-degree angle. You have a 90-degree angle. But oh, that's funny. Because on the page, I see a 60 degree and I see a 90 degree. Didn't we say that the other angle has to be 30 degrees? Oh, isn't that just this angle? I'm not going to be able to rotate it because there's so many different parts. But wouldn't that just be this triangle rotated? So the smaller side we said was 1/2. The longer side here we said was radical 3 over 2. We already solved that. So your x value here is going to be 1/2. The longer side, or the height, radical 3 over 2. And that is all you need to do. And then you could start making your reflections, right? Again, this is the same y value, so the y value stays the same. This is going to be the same distance, but because it's on the left side, right, it's going to be negative. So you negate the x. Okay? Now what about this? Look at this. It's the same x value that stays the same. So the x value will be the same. And you're going to negate the y value. The only thing I could say about being careful with is making sure you're going that same distance. It has to be a reflection, right? So make sure you're using the correct reflected point. And the other thing was, it really doesn't matter. You could either use the same y value or you could use the same x value, right? Depends where you start. So in this case, I'll use the same x value. So you have the same x value, radical 3 over 2, negate the y value. And look at that. You could either memorize it 3, 2, 1, 1, 2, 3, or you could do all this work, derive it, and then, use the reflections to find the rest. Now, we're going to find out kind of why this is so important to trigonometry. And again, trigonometry is study of right triangles. We just used right triangles to try to find this, right? And we're going to see where sine, cosine, tangent are coming from. Just a few things to remember, right? Before we go into that, let's start evaluating. So, sine of 30 degrees. And we're not going to continue to do what we're about to do on each of these, but sine of 30 degrees. Right now, all you know of sine is that, or cosine or tangent, is that we can make a right triangle. And in SOHCAHTOA, sine is opposite over hypotenuse. So, we said that this height here is 1/2. We said that this length here is radical 3 over 2. And sine is opposite over hypotenuse. So your opposite side is 1/2. Your hypotenuse side is 1, right? Because it's the unit circle. Oh, 1/2 over 1 is just 1/2. But isn't that your y value here? Right? What if I said sine of 45 degrees? Wouldn't the radius still be 1? So the hypotenuse would still be 1? So wouldn't it just be your y value over 1? Wouldn't that just be radical 2 over 2? The same thing goes for this. The hypotenuse would still be 1. So wouldn't it just be the y value? we just learned that sine is your y value. So xy so rather than doing all this work, right? Sine is your y value. Sine of 30 is 1/2. Sine of 45 is radical 2 over 2. Sine of 60 is radical 3 over 2. What about cosine? Let's find cosine. So, again, all we know of cosine right now is the right triangle. Cosine of theta is adjacent over hypotenuse. Your adjacent side is the neighboring side. So that's going to be this length here, which we said was radical 3 over 2. The hypotenuse, the hypotenuse it's a unit circle, so we know it's 1. Radical 3 over 2. Oh, so isn't that just the x value? What about this triangle right here, 45 degrees? It would be this length, right, the adjacent side, so radical 2 over 2, over the hypotenuse. The hypotenuse of a unit circle we already said was a radius, it's 1. So wouldn't that just be radical 2 over 2? And same thing for 60 degrees. Wouldn't it be 1/2 over 1, which is just 1/2? So cosine must be your x value. So now we see how the unit circle is so useful, right? Now we could evaluate sine. We could evaluate cosine. And something else, right? Tangent. Tangent's going to be a little bit more work. Tangent in SOHCAHTOA is opposite over adjacent. So for 30 degrees, the opposite side is your height, which is 1/2. And your adjacent side is their length, which is x, radical 3 over 2. But didn't we say that sine of 30 was 1/2? And didn't we say that cosine of 30 was radical 3 over 2? So isn't tangent just sine over cosine? So in the case of a unit circle, your opposite is your sine. Your adjacent is your cosine. Your y value is your sine. Your x is your cosine. Right? All of these things are related. So for the sake of doing the problem, let's just do it. Keep change reciprocal or keep change flip. So keep 1/2, change the multiplication, flip. 2's cancel out. Tangent of 30 degrees would be 1 over radical 3. You could memorize it as 1 over radical 3, or you could radicalize your numerator. So you multiply by the radical in the denominator over the radical in the denominator. So it's 1. And you would get radical 3 over 3. You'll see why I think it's an okay idea to memorize it as 1 over radical 3 in a second. Again, now you know that tangent is just sine over cosine. So we already have sine of 45. We already have cosine of 45. So you're going to do, so tangent of 45 would be radical 2 over 2 over radical 2 over 2. What's anything divided by itself? Oh, that's 1, right? What about tangent of 60? You're going to take radical 3 over 2 over 1/2. So do keep change flip. 2's cancel out. You get radical 3. So the reason I said if you don't want to radicalize the numerator, it's because it's kind of easy to memorize that way. 1 over radical 3, radical 3. Alright? And if you think about it, it makes sense because we said that your 30-degree triangle is just the reciprocal of that 60-degree triangle, right? They're the same triangle. So that's why it's the reciprocal for tangent. Okay. So the reason we'd use 30, 45, and 60, those are just your famous trig angles. They give you a nice proportion, even though these are irrational numbers. So if you put that in the calculator, it would be just a long, non-repeating, non-terminating number. You're able to see it in a nice, simplified form. So that's the reason we use those. What about all of these here now, right? We're going to find this quickly now, because now we know what sine is. We know what cosine is. Again, we just learned xy on a unit circle is just cosine sine. Cosine is your x, sine is your y. So, remember, when I said the way you can memorize it, 3, 2, 1, 1, 2, 3. Remember, 3, 2, 1 is your cosine, 1, 2, 3 is your sine, right? It's important you memorize that xy is cosine sine. So, sine of 0 degrees. 0 degrees. Sine is your y. So isn't that just 0? Cosine of 0 degrees. That would be your x, so it's 1. Sine of 90 degrees. That would be your y value, so it's 1. Sine of 180 degrees, your y value, 0. Sine of 270, your y value, -1. Sine of 360, 360 is coterminal with 1, with 0 degrees. So it's 0 again. What about cosine now, right? Cosine we said are our x values. So cosine of 0, 1. Cosine of 90, 0. Cosine of 180, -1. Cosine of 270, 0. Cosine of 360, it's coterminal with 0, so it's 1. Tangent. Didn't we just learn that tangent is just sine over cosine? So 0 divided by 1, 0. 1 divided by 0, that's impossible, right? Does not exist. 0 divided by -1, 0. -1 divided by 0. You can't divide by 0. It does not exist. 0 divided by 1, 0. So, we will get into graphing. Let me see. That's not the next one. Okay. We're eventually going to get into graphing, right? But just to kind of show what these things kind of look like. So 1, -1, these are your basic trig functions. 0, 90 degrees, 180 degrees, 270 degrees, 360. Sine of 0 would be sine of 0 is 0, we said. I'll put a little blue. Then it goes up to 1, then it goes down to 0, then it goes down to -1, then it goes back to 0. This would be what sine looks like, right? And that's your basic sine function. Notice it's a wave. That's why it's called a sinusoidal function. It takes the form of a wave. Cosine starts at 1, goes down to 0, goes down to -1, goes back to 0, goes back up to 1. So it looks like that. Something you might notice, they both oscillate between -1 and 1, right? So if I was actually to move this, wouldn't this be directly on top of the other function, right? So technically sine and cosine pretty much are the same function. You could always shift a sine function to be coterminal with a cosine function, or vice versa, but it depends where the starting point is, right? And then lastly, tangent has a lot of spots that it doesn't exist on, right? This is where you're going to have some asymptotes. So I'll do tangent in purple. So at 90 degrees, asymptote. At 270 degrees, asymptote, right? Why is there an asymptote there? It was when your denominator was 0. So what had to equal 0? Cosine had to equal 0, because tangent is sine over cosine. So this is actually what that would look like. Let's graph where it's 0 first. So it's 0 at 0. And also notice that whenever sine is 0, tangent is 0. Because it's sine over cosine. So this is actually what this will look like. It approaches but never touches those asymptotes. So that would be your tangent function. Again, what we said before though, sine and cosine, they could be coterminal. They could be exactly on top of each other if you shift it in the right way, right? Can tangent do that? No. What did I call sine before? Sine is a sinusoidal function. It takes the shape of a wave. Cosine is also sinusoidal. It takes the shape of a wave. Tangent? No, not sinusoidal. It's actually a fraction. So when a function is represented by a fraction, what do we call that? Tangent's actually a rational function. It just has infinite asymptotes. Okay, that was just a quick little demonstration of, graphing. Those are the basic trig functions, right? Something that we could talk about with the basic trig functions when you're graphing them. One full cycle, right? Let's look at sine here. So you start at 0, you're going to go up, around, down, back around, and you're back at where you started, right? So it takes 360 degrees to show one full cycle. One full cycle we call a period. So a period of a basic trig function would be 360 degrees. More commonly, we talk about it in radians. Remember, we said that 360 degrees is just 2 pi radians. So your basic trig function has a period of 2 pi. Okay. Evaluating trig functions. So we have sine here. Remember, in sine, sine we know is opposite over hypotenuse, right? So since it's going to be proportionate, you could say this is your opposite, this is your hypotenuse. It also says that it terminates in quadrant 2. So rather than trying to visualize this in my head, what we're going to do, let's sketch this out. Quadrant 2 is right here. Trig is the study of right triangles. Let's make a right triangle. Let's call this angle theta. Remember, we're using the reference angle, right? That's why it always has to be with the x-axis. And again, sine opposite over hypotenuse, right? So, ka, toa. So, our opposite is going to be 52. Our hypotenuse is going to be 173. Let's try to find the missing side. Since it's a right triangle, we could use Pythagorean theorem. A squared plus b squared equals c squared. X squared plus 52 squared equals 173 squared. If you want, subtract that on both sides. So 173 squared minus 52 squared. You get x squared equals 27,225. Square root of both sides. Get the square root of that number, and you get 165. So now, tangent in SOHCAHTOA, tangent is opposite over adjacent. So your opposite side, we said, was 52. Your adjacent side is 165. Are we done? No. Right? We found tangent of the reference angle, not what this original unknown angle is. Right? So, to find tangent of the original unknown angle, what you're going to do is do all students take calculus. That's something I actually wanted to show a little bit before. What I was saying before, right? Quadrant 1, you have a point, the points are positive, positive, right? That's in any graph. So that means your sine is positive, right? And your cosines are positive. Tangent is just sine over cosine. Positive divided by a positive is positive. So that means sine, cosine, and tangent are all positive, right? What about here? The only thing that's positive is the y value. We said that your sine is your y value. So sine is positive, cosine is negative, tangent is sine over cosine. So positive divided by a negative, that's negative. So only sine is positive here. What about this? Sine is negative, cosine is negative. But tangent, sine over cosine, negative divided by a negative, that's positive. So only tangent's positive here. In this case, for quadrant 4, you have positive, negative. So the only thing that's positive here seems to be cosine. What about tangent? A negative divided by a positive would be negative. So we could create an acronym, right? In this case, it's all the trig functions are positive. So all, in this case, it's only sine. All students, S for sine, take calculus. All students take calculus. So that means quadrant 1, all of the trig functions are positive. Quadrant 2, only sine is positive. Quadrant 3, only tangent's positive. Quadrant 4, only cosine's positive. Again, I'm trying to go deeper into the concepts and where they come from. If you just remember all students take calculus and you remember that's what you have to do in the last step of every trig problem, then so be it. You don't have to know the deeper concept, but it is nice if you do know it. So all students take calculus. We're finding tangent. Is tangent positive there? No. So, since you use the reference angle, we know it's the same absolute value, right? But we have to make it negative. So tangent of theta would be negative 52 over 165. Okay? You're going to see, when we do the reciprocal trig functions in this video, you're going to see that we're basically doing the same problem. It's just with the reciprocal trig functions. Okay. Inverse trig functions. So, again, with trig, it shows a relationship, a special relationship between the sides and the angles, right? So sine of theta, theta is just some angle that we're using a Greek letter to denote. Sine of theta equals opposite over hypotenuse. But look at that inverse word, right? Remember when we learned inverse, all that did was switch the x and the y. So you're switching the input and the output. So if you're finding the inverse, that little negative 1, remember when we learned inverse, we would choose, if I said put an exponent of negative 1 on that f, or a superscript I should say, it's not an exponent. That's saying the inverse of f of x, right? The inverse of sine of, and remember, inverse, you switch your output and your input. So the inverse of the opposite over the hypotenuse equals theta. So if you're ever trying to figure out the angle, you could just use your inverse function. On your calculator, that would be second and then whatever trig function you're using. So in this case, for sine, if you wanted to find what the angle equals, you would do the inverse of sine of the opposite over the hypotenuse. In the case of cosine, the angle would equal the inverse of cosine of adjacent over the hypotenuse. For tangent, the angle would equal tangent, the inverse of tangent, of the opposite over the adjacent. Alright? You don't have to memorize this. You just have to know the inverse function gives you the angle. So if you're ever trying to solve for the angle, you just do the inverse trig function. Second, and then the trig function on your calculator. So in this case, AB is 42. BC is 31. We want to find the measure of angle A. So we're given the opposite. We're given the adjacent. So opposite, adjacent. Which trig function's opposite and adjacent? That would be tangent, right? So tangent theta equals your opposite, 31, over adjacent. We want to find the angle. If we're trying to find the angle, you have to use the inverse trig function. So when you take the inverse of any function, you switch the input and output. Put that in your calculator. What I'm doing, second tangent, 31 over 42. And I get, oh, I'm in radian mode. These answers are in degrees, right? So let me just make sure I'm in degree mode. We get 36.43085.812. So about 36 degrees. That's how you use your inverse trig functions. Now for graphing trig functions, it's so important that you know this form. This is the most general form of a trig function, right? Remember, you could remember it as your transformations, but it is kind of important that you know the vocab as well. So let's go into the vocab, right? A is your amplitude, right? B, we'll go into B last, just because B is indirect. C is your phase shift. D is your midline. And B indirectly gives you your period. Okay? If this is sine, it starts at the midline, right? If it was negative sine, still starts at the midline, but it would go in the opposite direction, right? If this was cosine, starts above the midline, but if it was negative, then it would just reflect over the x-axis. It starts at the minimum, right? So we'll go into it when we graph things as well. But let's say we had this sine function here, right? Whoops. Let's say we have this sine function. Your midline splits it directly in the middle, right? So this here would be D, right? Your midline would be y equals D. Your amplitude would show you the distance from the midline to the peak, or the distance from the midline to the minimum. So it would be that length A, right? Your phase shift, let's talk about period first, actually. Period, B is not your period. B indirectly gives you your period. You have to memorize that formula, 2 pi over B, right? Your period is 1 full cycle. So in this case, your period is 2 pi over B, because we're using the abstract form. C is your phase shift, right? In this case, it didn't shift left or right. It started at 0. So your phase shift was 0, right? But if it were to shift, then that would be your C, right? If I were to move this, so let's say this shifted to the right, your C would be C. So right here would be C, your phase shift, right? Because it shifted to the right. So again, it might look confusing because we're using all abstract terms, A, B, C, D. When we have numbers, it might make a little bit more sense, okay? It's just important to know what those things mean. So if you want to pause this and, look at what each of these things are, you can. If you need to take a screenshot, take a screenshot. I know it's in your notes. It's in your reference sheets. All right? But we're going to move on. So, graphing trig functions. Your period. We said that a period is 2 pi over b. In this case, your b is 6. So 2 pi over 6 is just pi over 3. Your frequency is the reciprocal of your period. It's 1 over your period. So rather than pi over 3, your frequency is going to be 3 over pi. Your amplitude is your A. Amplitude is 2. Your phase shift, nothing is attached to x in the parentheses by addition or subtraction. So your C is going to be 0. It's going to start at 0. It doesn't shift. Vertical translation, it goes down 3 units. So it shifts down 3 units. Equation of midline, that's just your vertical translation. So y equals -3. Your sketch point, that's going to give you the perfect points where it hits the midline, where it hits the maximum, where it hits the minimum. So your sketch point follows the formula period over 4. So your period we said was pi over 3 over 4. Keep, change, flip. So keep pi over 3. Change to multiplication. Flip 4 to 1/4. Pi over 7. You always start at the phase shift. So the phase shift was 0. We're going to go up by pi over 7. So 1 pi over 7, 2 pi over 7, 3 pi over 7, 4 pi over 7. Oh. Huh, that's embarrassing. 3 times 4 is 12. So, pi over 12. 2 pi over 12. 3 pi over 12. 4 pi over 12. It is very late, okay? And I'm not editing that out. So, 0. Pi over 12. I'm just going to simplify these. Pi over 6. Pi over 4. Pi over 3. When there's no phase shift, that fifth point is going to be the same as your period, right? Because it's going from 0 to the period. But if the phase shift shifts, it's not going to be the same. So don't rely on that. So it says just show one full period. So I'm just going to make this as evenly as possible. We know these values, right? This is 0, pi over 12, pi over 6, pi over 4, pi over 3. Think about this now. The midline we said is -3. The midline is -3, right? What about the maximum and the minimum? Doesn't the amplitude give you how much higher it goes and how much lower it goes? So -3 plus 2. -3 minus 2. So now we have the maximum and the minimum points. So we have the perfect points where they're going to land. And we have the max, the midline, and the minimum. This is a sine function, right? Sine starts at the midline. If it was cosine, it would start at the maximum. Unless they're negative, and then you would flip both. Right? So it's sine. We start at the midline, -3. So we know we're going to have -1 on here, -2, -3, -4, and -5. So -1, let me use a different color. So -1, -3, -5. I like to draw my midline. And let's draw our function now. Starts at the midline. This is a positive sine function, so it's going to go up to the maximum. It's going to go down to the midline, go down to the minimum, go back up to the midline. One full cycle. So again, to show what these things mean, right? One full period. In this case, it's one full cycle, your period. Your period, we said, was pi over 3. Isn't from 0 to pi over 3, isn't that just pi over 3 the distance? So that's your period. Your amplitude is 2. Look at that. It's from the midline to the maximum or the midline to the minimum. That's 2 units. That's your amplitude. Your midline is what splits that directly in the middle. The phase shift is where it starts. It started at 0 in this case. Or where it shifts to. It didn't shift. Frequency. Now this is why it's so important that before when we showed the basic trig functions, right? We said that the period of a basic trig function would be 2 pi, right? So it says here that the frequency is 3 out of pi, right? So let's say we wanted to make the denominator 2 pi, right? You could multiply by 2 over 2. You'd get 6 over 2 pi. That means that this would continue 6 times before it would. That would mean that it occurs 6 times within the basic trig function. So how a trig function would take 2 pi just to complete one full cycle, this would take 6 times within that 2 pi. That's what a frequency means, how many times it occurs, how frequent it occurs. All right? We'll do it again. And this is an actual region question, this one. So we have our amplitude. We have our midline. Right? The midline is at 2. It says it wants us to graph it over 2 pi. So the midline is 2. I like to draw my midline. The amplitude is 3. So for midline is at 2. Your maximum and your minimum will be 3 up and 3 below the midline. So 5, -1. This is a sine function, so we're going to start at 0. And we know the heights, right? But we don't know the x values. So we're going to have to actually solve for the period and then the sketch point. So, period, remember, equals 2 pi over b. Your b in this case is 2. 2 cancels out. Period is pi. So, in 2 pi, we're going to see 2 full cycles, right? So the frequency is actually going to be 2 over 2 pi. But the sketch point is what tells us those perfect points. So sketch point, remember, is period over 4. So pi over 4. We start at the phase shift. Is there anything attached to x by addition or subtraction? No. So we start at 0. Go up by pi over 4. Another pi over 4. 2 pi over 4. 3 pi over 4. 4 pi over 4. Simplify. And I just showed one full cycle, but they actually want us to show till 2 pi. So if we only got up to pi, we're going to have to double this. Alright? So we actually have to show 10 points. So let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so we could skip by 2s. So you have pi over 4, pi over 2, 3 pi over 4, pi. We know it's going to go to 2 pi, right? If you wanted to keep going, like label them all, you could keep going up. Like this would be 5 pi over 4, right? This would be 6 pi over 4, which simplifies to 3 pi over 2. This would be 7 pi over 4, 8 pi over 4, which would just be 2 pi. Okay. So, again, this is sine, so you start at the midline. It's not negative, it's positive on the outside, right? So we're going to go up. So up to the max, down to the midline, down to the minimum, up to the midline. That's one full cycle, right? But it wants us to continue this to 2 pi. So this is where it gets easy, right? You just have to continue the pattern. Again, what do these things mean, right? We already have our midline. The amplitude is just the distance from the peak or the minimum to the midline, right? One full period is pi, right? But what's that frequency? Now we could actually show the frequency since it's out of 2 pi, which is your basic trig function. How many times did it occur? How many full cycles did we show within 2 pi? Your frequency is actually 2, because there was 2 periods shown. Frequency would be 2 out of 2 pi, which is just 1 over pi. Remember what I said before. isn't frequency just the reciprocal of the period? That's 1 out of pi, right? Okay. Now your reciprocal trig functions, don't get confused by these things, right? It's very simple. Secant is 1 over cosine. Cosecant is 1 over sine. Cotangent is 1 over tangent. A way to memorize this, right? Cotangent has tangent in it. 1 over tangent. Now this is the one that really confuses people. This starts with a C, but it's sine. Students often will say 1 over cosine because they think that it's the same. Cosecant is 1 over sine. So, just remember it's the opposite of what you would think. Right? Unless you just memorize it. Secant starts with an S, but it's actually 1 over cosine. It's not 1 over sine. Okay? Now, there's really two things you could do with these questions. You could either find cosine and then just do 1 over cosine, or you know that cosine is adjacent over hypotenuse. So 1 over that would be 1 times hypotenuse over adjacent. So 1 times that would just be that, right? Hypotenuse over adjacent. So if cosine is adjacent over hypotenuse, then secant would be hypotenuse over adjacent. Sine is opposite over hypotenuse, so cosecant would be hypotenuse over opposite. Tangent is opposite over adjacent, so cotangent is adjacent over opposite. Again, if you don't like doing it that way, you could just find tangent and then do 1 over that. Alright? That's all this is. It's the same exact thing as what we did before. So, let's do what we did before. Third quadrant. Draw your quadrants. Third quadrant, that's where the terminal ray is. Make a right triangle. Theta is going to be the reference angle with the x-axis. It's only a reference angle. We're not actually using the original angle, even though they didn't give the original angle. So, and by the way, in this case, it's actually alpha. So rather than use theta, I guess technically you should use alpha, but it's not going to make it wrong. So, in SOHCAHTOA, what is TOA? Opposite over adjacent. So, your opposite will be 7. Your adjacent will be 9. We want to find cosecant, which is 1 over sine alpha, right? Cosecant is 1 over sine. We're going to have to find the hypotenuse. So we use Pythagorean theorem. A squared plus b squared equals c squared. X is your hypotenuse. So 9 squared plus 7 squared equals x squared. 9 squared plus 7 squared, 130. Take the square root of both sides. It's not a nice number. Let's check if there's a perfect square in there. No perfect squares. So, x is radical 130. So, we're trying to find, well, I'll show you both ways, okay? So first, sine of alpha would be your right? Opposite over hypotenuse. So the opposite is 7. Hypotenuse is radical 130. You would do, all students take calculus. Sine is negative, right? But we're not looking for sine. We're looking for 1 over sine. So cosecant of alpha equals 1 over sine, which would be 1 over negative 7 over radical 130. which would just be 1 times negative radical 130 over 7, you would get negative radical 130 over 7. That's your answer, right? One way of doing it. We're going to do exactly the same thing now, but rather than finding sine first, you're just going to find cosecant. So, since sine of alpha is opposite over hypotenuse, then cosecant of alpha will be hypotenuse over opposite. So what is your hypotenuse? Radical 130. What is your opposite? 7. All students take calculus. In quadrant 3, is sine positive? No. So if sine isn't positive, its reciprocal function wouldn't be positive. 1 over a negative is still negative. Right? So again, whatever you think you're going to be able to do, you do it. Alright? Okay. Evaluating these numbers, and we're using these famous angles here. So, cosecant. 1 over sine of 30. What is sine of 30? Oh, 30 degrees, that's in quadrant 1. I should have that memorized, right? Remember. 30, 45, 60. 3, 2, 1. 1, 2, 3. They all are over 2. And they all have a radical in the numerator. You don't have to include the radical on the 1 because square root of 1 is just 1. Sine is your y value. So that would be 1 over 1/2. Same as saying 1 times 2 over 1. 1 times 2 is 2. Answer would be 2, right? This is how you should be thinking about it, right? You're not going to have the unit circle on your test. You could put this in your calculator, sine of 30, but the problem is, what if it was sine of 45, sine of 60? Then you need to know that it's radical 3 over 2. You need to know it's radical 2 over 2. You can't, with the 1/2, it's easy. It's going to be 0.5 in your calculator. But when you get radical 2 over 2, radical 3 over 2, it's going to give you some crazy number. You don't know what that is. Unless you memorize that the answers are either radical 2 over 2 or radical 3 over 2, and then you put that in your calculator as well just to verify, right? I'm trying to give you options, but this is how you really should go about it if you understand it. Cotangent, 1 over tangent. So 1 over tangent of 90 degrees. 90 degrees is one of those really nice points that we were able to just figure out, right? So for a unit circle, we know the radius is 1, so 0, 1 would be the point. Cotangent, 1 over tangent. Slight problem, right? Tangent is sine over cosine. So, what you're going to do, take the reciprocal of that, 1 times cosine over sine. Cosine in this case is 0, sine is 1. 0 over 1 equals 0. You get 0 degrees. Right? Okay. Secant of 180. 180 is one of those nice angles, one of those nice points that you could figure out, right? Again, this would be -1, 0, right, for 180 degrees. Secant is 1 over cosine. So, cosine of 180 is the x value, -1. 1 divided by -1, -1. Right? Now, you could go about the radian measures in different ways. Personally, I recommend that you convert 2 degrees, but something you could do to kind of memorize the radians for the first quadrant, if you're memorizing the first quadrant, right? You know, it's 30, 45, 60, right? This is pi over 3, pi over 4. This is pi over 3. This is pi over 6. Again, very late right now. And the reason that the way you can memorize that, right? You know, 3, 4, 6. The one that is going to be the bigger number would be the one that's divided the least, right? The 45, you could see the 4, right? Even though that's not y, it's 4. It's just the way to memorize it. And then the one that's divided the most is going to be the smallest, right? So 1 over tangent, you're going to have to take, you know, the cosine and the sine value. So we know that pi over 3 is going to be 60 degrees. But again, very easy to make a mistake by just going based off your memory. So I recommend converting 2 degrees first. So remember to convert from degrees, it's on your reference sheet. But usually radians have pi in the numerator. You want to get rid of that. So it's going to be 180 over pi. 180 divided by 3 is going to be 60. So cotangent of 60 degrees. 1 over tangent of 60. That's the same as saying 1 over sine of 60 over cosine of 60, which is the same as saying cosine of 60 over sine of 60. If we were to, you know, put that on our calculators, right? I mean, you guys know, if you memorize that chart from before, tangent of 60 was tangent of 60, right, was radical 3. So cotangent of 60 would be 1 over radical 3, right? But the way you can memorize it, right? 3, 2, 1, 1, 2, 3, all over 2, all have a radical in the numerator. Should just leave it on the screen. But 60, 45, 30. Cosine is the x value. Sine is the y value. Keep, change, flip. 2 cancels out. You get 1 over radical 3. So we actually did, you know, show multiple ways of doing this one. Okay. Let's convert from radian to degrees. 3 pi over 2 times 180 over pi. Pi cancels out. 180 divided by 2 is 90. 90 times 3 is 270, right? Cosecant of 270 degrees is just 1 over sine of 270 degrees. 270 degrees is one of those nice points, right? This point would be 0, -1. Sine is the y value, so -1. 1 divided by -1, -1. Lastly, 5 pi over 4. Let's hope that it's not such a nice point. So 5 pi over 4, convert to degrees. 180 over pi. You're going to multiply by, pi cancels out. 180 divided by 4. I think it's 45, right? Yeah, 45. 45 times 5 is 225. It's not such a nice point. Nice. So secant is 1 over cosine. 225, I don't have memorized. But I do have my first quadrant memorized. And something that's really easy to do, find the reference angle, right? So 225, we know this is 90 degrees. This is 180, this is 275. And it's going to be in quadrant 3, that terminal ray. Make a right triangle, right? Or you don't have to make a right triangle. The reference angle is the positive acute angle between the x-axis and the terminal ray. So this angle here we said was 225, right? So the bigger angle is 225. The smaller angle here that we want to get rid of is 180. So you're going to do 225 minus 180. You get 45. So the reference angle is 45 degrees. Don't we have that memorized? What's cosine of 45 degrees? It's the x value. Radical 2 over 2. So 1 over radical 2 over 2. But it's cosine, right? So what do I have to do? All students take calculus. Quadrant 3. This is why it's important that you remember the original angle. It's 225, right? Because now, 225 cosine, we know it's quadrant 3. So, cosine, is that going to be positive or negative? Only tangent's positive here. So negative. The reciprocal of that would be negative 2 over radical 2. That's your answer. That was a fun one. Should have done more like that. Okay. Okay. Lastly, trig identities. Now, throughout the year, I taught you guys most of the trig identities, right? I also derived most of them. On the Regent, they really only talk about Pythagorean's identity, right? Now, something that's kind of cool about Pythagorean's identity, right? We said before on the unit circle, right, that sine is your y value, right? And cosine is your x value. So you know that the sum of the legs equals 1 squared, or equals your hypotenuse squared. That's Pythagorean's theorem. So a squared plus b squared equals c squared. In this case of a unit circle, right, cosine is your x, your a. Sine will be your b, or vice versa. And then c has to be your hypotenuse, which is 1. So we have this trig identity. Sine squared plus cosine squared equals 1. That's Pythagorean's identity. That's where it comes from. Okay? And the good thing about the Regent with these kind of questions is they always provide that for you. If you didn't want to use the identity, you don't have to. You could draw it out exactly how I showed before, right? This is just negative 7 over 10. We know cosine is adjacent over hypotenuse. So it would be 7. So adjacent would be 7. Your hypotenuse would be 10. We're finding sine, right? No, find the value of tangent. So you would still have to find, your opposite side. And then you would have to do opposite over adjacent. That's something you could do. You don't have to use the identity. It does ask you to use the identity, though. And it's much easier to use it. So, sine squared theta plus cosine squared theta equals 1. Cosine is negative 0.7, so negative 0.7 squared plus sine squared equals 1. You could subtract that on both sides. You get sine squared of theta equals, let me put that on my calculator, 1 minus negative 0.7 squared, 0.51. Take the square root of both sides. I get kind of a wild number. I'll just leave it as 0.51 for now. It says it's in quadrant 2, right? So, all students take calculus. I mean, we did use the identity, so the sign should come out correctly. But we know it's going to be positive because it's in quadrant 2. Tangent of theta equals cosine of theta, sine of theta over cosine of theta. If you guys hear my dog snoring, it's because I put her to sleep with the math. But sine theta, radical, 0.51. Cosine of theta, negative 0.7. Put that in your calculator. I mean, that's your answer. But put that in your calculator. You end up getting negative 1 point. It's really weird. I don't know what that is. Negative 1.020204061 says to the nearest hundredth. So, negative 1.02 would be your answer. Okay. So that was an overview of everything that we learned in trig that you really should know for the regent. I really recommend, watching these videos, writing down any questions that you have, and then when I do my virtual lessons, asking them, because we could go deeper and it could be, more focused on what you understand and what you don't. But yeah, hope this helped. Thank you for watching. Good luck on the regent.